Welcome back. I hope that your mental stack has not overflown because of all the recursion. So in this second part, we'll keep it very light. And in particular, I will help you with some of the exercises that are on the website for this chapter. In the very first lecture, we showed very quickly an implementation of quicksort in Haskell. And what we will do now is we will look in a little bit more detail at quicksort in Haskell. And quicksort, the idea of quicksort is to sort a list recursively by decomposing the list somehow, recursively sorting those lists and then combining the results together. And if we think about that for a little bit, we can say, if I have the empty list, it's already sorted. And now how do we recurse, how do we break up that list into two parts that we can recursively sort and then easily combine the results to get a sorted list? Well, what we do is if we can look at the head of the list and break this list in two, one with all the values that are less or equal than the head, one with all the values that are greater than the head, then we can just, recursively sort those two lists and inject the head in the middle, and we're done. And that's the kind of the algorithmic essence of quicksort. But as I already warned you, in the real implementation, you're not creating new lists. You're really mutating the data structure in place to swap the elements. And that's an aspect that this version of quicksort doesn't show, but it does show this kind of recursive structure. All right, here's the implementation of quicksort. Similar to the very first lecture, only now it's called quicksort instead of F. So what we do, when we have the empty list, it's already sorted. When we want to sort a list, X, cons X's, we create a list with all the elements that are smaller or equal than X. And for that, we use a list comprehension. We create a list of all the elements that are larger than X. We sort both of those, and we put X in the middle. So this is a very simple implementation of quicksort, but again, it's also a very simplistic implementation of quicksort. But if you want to understand the structure, this is probably a very good illustration. If we want to illustrate how this works, let's abbreviate quicksort as Q, such that the slide doesn't overflow. So we want to sort the list 3, 2, 4, 1, 5. What we're going to do is we're taking the head 3, and we're going to break up the rest of the list into the elements that are less than equal to 3 and the ones that are larger than 3. So the elements that are less in this list are 2 and 1, and the ones that are larger are 4 and 5. So that's what you see. So we recursively sort those, and we inject 3 in the middle. If we sort the list to 1, we take the head, we split the remaining list, which is just 1, into the values that are smaller and the values that are larger. So the ones that are larger, that's the empty list. The ones that are smaller, that's 1. And then we drop 2 in the middle. Same on the right-hand side. We take the first element and we split the remainder of the list, which is just 5, in the elements that are larger than 4. So that's the list 5, and the elements that are smaller, which is the empty list. And we inject 4 there in the middle. Okay, now the empty lists here and here are already sorted, so nothing to do there. We just have to sort the list of one element, and you can verify that when you sort the list of one element, it returns that list itself. So if we make those recursive calls there, we get this list, and now you see that the result is 1, 2, 3, 4, 5. Okay? You just kind of walk that tree to get the result. Okay. That was quick, short. The exercises for this week, there's a lot of exercises to define functions recursively. But I'm going to do just a couple of them here with you. So let's look at the first one here. So it says, produce a list with n identical elements. So that's a function that takes an integer, which is the n. Then it takes a value, a, and it should return a list of n copies of that value a. So how do we do that? Well, we do that by not we don't recurse over this a, and we have to build a list. So what we have to do is we have to define this recursively over the structure of this integer. So we have two cases. N equals 0. If I replicate an element 0 times, well, I get the empty list, so that case is easy. So if I want to replicate a value n times, what do? Well, I first replicate it n minus 1 times. So I get a list of n minus 1 times a's, and then I cons a on top. So that one is easy. But again, you have to kind of look a little bit, and then you see, I'm doing recursion over that guy. There's two cases. You just write them down, and everything drops out. Here is another friend of us that we've seen in previous lectures, and there I warned you that in Haskell, lists don't have constant time access, and when we implement this function, that will be very clear. So what we have to do is we have to take a list and a number, and then return the element in that list at that position. Of course, we can do this using a take or drop or other functions, but the goal here is to define it using recursion. And since we have here two recursive structures, the list and the integer, we're going to define this by recursing over both. Okay? So how would that look? Well, first thing is if we want to have the zeroth element of the list, well, that is the head of the list. All right, so if I have a list x cons x's, and this one is 0, then that's the element. So the first element of the list is the element at index 0. So that's a simple one. If the list here is empty, well, what do? That's a good question. So probably if I want to index the nth element of the empty list, that's going to give an error. So let's not worry about that. We're going to put that as the last clause. All right? So now we can assume that this one is not 0 and this one is not empty. If that one was 0, we're done. If that one was empty and this one is not 0, then we have an error. So now they're both non-zero. So what we do is we say, okay, if this is x cons x's and this is n, what we do is we take the index of the tail of the list, the n minus 1 index. So simple recursion too. It's just that we have to be a little bit careful about the base cases. And the last function we're going to define using recursion here decides if a given value is a member of a list. Of course, we can cheat here and not using recursion. We can easily use filter or list comprehension or something. But the goal here is to define this function using recursion. And in this case, there's an obvious candidate to do the recursion over. That's this list. So if we're looking for an element A in the empty list, that's false. That element is not in the list. If we're looking for an element A in the list x, axis, well, we have to check whether the head of the list is equal to the value that we're looking. If that's the case, we return true. If that's not the case, then we just search for that element in the tail of the list. And eventually the tail of the list will be empty, so we will hit the base case and we're done. Now you see here that since we're checking equality of this element to each head of the list until we find it, the type A must support equality, and that's what you see here in the type. So we can only search for a value in a list if the types of the list support equality, and that's why we get this constraint here. So A must be a member of the type class EQ of A. Great. So I hope that this helped, these small exercises. And as I said, on the website, there's a lot of exercises where you will do recursion. And if you get stuck, try eating a banana, and maybe it helps. Or maybe, you can eat 2 bananas, and that will work even better. See you next week.